Alright, welcome back everyone to CO673 CS794 Optimization for Data Science. This is our second lecture where I will be going through some of the basics in optimization. Okay, before we start, let me mention a few things. First of all, this is an overview lecture, meaning that we're going to go through the basics that you may or may not have learned before. So inevitably, this lecture is quite dense in terms of math. The good news is most of this lecture, will be repeated again in later lectures. Okay, so my hope is that by putting everything together, it will be easier for you to self-study. Okay, so later on when we discuss a specific point, you may easily go back to this lecture and refresh your memory. I also want to mention that I decided to have the overview lecture so that you can have a pretty good sense of what this course is about. Okay, so you can make up your mind, whether or not you should stay in this course. So please go over the first two lectures this week and decide if this course is suitable for you. Okay, because we have a quite long waiting list and would like to finalize the students before we start the assignment next week. Okay. On the other hand, if you feel a little bit overwhelmed in this lecture, this is normal. Okay, because you may not, depending on your background, you may not have learned some of the basics here, which is perfectly fine. But you have to self-study, go through the lecture very carefully by yourself. You don't have to do it in this week, because as I said, we don't need all of the lecture material in the next few lectures. So you have quite a bit of time to familiarize yourself. Okay, so don't feel overwhelmed if you find this lecture is a bit challenging. And of course, always feel free to post your questions on Piazza, right? So other students can help you, and me and TA can help you as well to digest the lecture material. Okay. So now let's get started. So for the most part of this course, our universe is a vector space. And the formal definition is given in my note. Here I'll give you some examples. And the reason we choose vector space as our universe is because it allows us to use linear algebra and multivariate calculus tools. Okay, it's quite popular and powerful. It took machine learning people or AI people a few years in the early 80s, 90s to realize that linear algebra and multivariate calculus are really the key to some fundamental problems in machine learning. Okay, so if you want to understand data science and machine learning, you really do need a bit of linear algebra and calculus. Okay, so I'm not going to bore you with the precise definition of a vector space. As I mentioned, it is in the note. Here I'll just mention what we mean by a Euclidean space. A Euclidean space is a special vector space where each vector is just a D tuple, meaning that we have D numbers and we just stack them together, okay? And we call it a D-dimensional vector. So here I'll give you an example where V is a D-dimensional vector. And we can define two operations. One is addition of vectors, right? If I want to add two vectors, I just add the corresponding entries. There's also a scalar multiplication, meaning that you multiply a number to a vector. And this multiplication is performed by multiplying this number to every entry in the vector. And this is what people call element-wise multiplication or element-wise addition. Okay, so these two operations, they satisfy some property. For instance, the addition is associative, the multiplication is associative, and it is distributive as well. We can define a zero vector where any vector when you add any vector to 0, you get the vector back. And once you have 0, you can define the negation of a vector. Okay, so I hope this is all familiar, and I'm assuming most of you have seen this before in a linear algebra course. Okay, so more specifically, a vector is just an array. If you are more of a programming person, like in computer science, a vector is just an array of real numbers, and we have the length or the dimension of the vector, and we use vj, this letter, to index the jth entry in the vector. Okay, and I want to emphasize that in math and also in junior, the index starts from 1, whereas in Python, the index starts from 0. Okay, in all of my lectures, my index always starts from 1. But if you're going to implement some of the algorithms in Python, you need to keep in mind Python index starts from 0. Okay, you have to do this exchange. And we have two vectors. One is called a row vector. This is what we define here. And we also have a column vector. A column vector is just a transpose of a row vector. So you basically put the entries in rows, right? So and typically when we write a vector, I prefer to write this way because it takes less space. But really, a row vector and a column vector, how you write or how you represent these two vectors. And if you think of a vector as a matrix, which I will define in a minute, a row vector has size 1 by d, so we have one row and then we have d columns, right? A column vector, on the other hand, have d rows but only one column, sorry. Okay, and by default, when we refer to a vector, we usually mean it's a column vector. Okay, and sometimes it doesn't really matter if it's a row vector or if it's a column vector, because there's no confusion. All right, so once we have two vectors, then we can define the dot product or the inner product of two vectors that are of the same size. They have to be of the same size. I don't care if they're row vectors or column vectors. Okay, I define the inner product with this angle notation. So the inner product is defined as the summation of the product of the corresponding entries in the two vector. Okay, so it's a very simple definition. As you can see, the dot product of two vectors is a number, a real number. Okay, it's not a vector anymore. The dot product is a number. And we say two vectors are orthogonal using this notation if the dot product between them is 0. Okay, so if I draw a picture, if you have two vectors, right, if I have a vector like this and I have another vector like this, then they're orthogonal, right? The dot product would be 0. Okay, and you can easily verify from this definition here, you can easily verify that the dot product satisfies the following properties. First of all, it is symmetric, okay, and it is, I have a typo here, this should be U. So if you take the dot product between a vector and itself, it is always non-negative, and it is 0 if and only if the vector is 0. Okay, and then we have linearity, namely that if you add two vectors, then the dot product with respect to a third vector is just the sum of the two dot products. And if you scale a vector, then just scale the dot product correspondingly. Okay, so these three properties in fact give you an abstract definition of dot product, and the one we see here is a special case. Okay, for the majority of our course, this definition is enough. This special case is enough. Okay, and you can try to prove the Koch-Schwarz inequality. This is very crucial, and we're going to use this inequality many times in this course. Okay, so what it says basically is, if you take the dot product between two vectors, then it's upper bounded by the square root of the dot product of one of the vectors, and multiply the square root of the dot product of the other vector. Okay, and the way to prove this is to use the fact that U minus V dot product U minus V is greater than 0, right? And I'm going to use linearity. So this can be written as U minus V and subtract V minus V. And I'm going to use symmetry, and then I'm going to use linearity again. I'm going to get UU subtract UV subtract VU, which is just UV, doesn't matter because it's symmetric, and add VV greater than 0. Okay, and this inequality here comes from positive definiteness, right? This will not give us this inequality. Will not give this. Will not quite give us this, and I leave the. But this is the main idea to do the proof. Okay, I leave the rest to you. All right. So now we have the dot product between two vectors. And the next thing I want to recall is a matrix. So a matrix, like a vector, so if a vector is a one-dimensional array, then a matrix is a two-dimensional array. Right? In this example, we have a matrix A, which is m by n matrix, meaning that it has m rows and n columns. Okay, and we sometimes write the matrix as a collection of columns, so we have n columns. Okay, or we write as a collection of m rows. Okay, and you have noticed that I'm using the notation A column j as the j's column vector of A, and I'm using AI column as the row of the matrix A. Okay, and I'm going to use Aij to index the ij's entry of the matrix A. And you can define the matrix transpose. So the matrix transpose, basically you take the first row and you put it in the first column. You take the second row, you put it in the second column. You take the last row and you put it in the last column. Okay, so in other words, you're going to flip dimension. Okay, and we see a matrix is symmetric if A equals A transpose, and this can happen only when m equals n. So you have the same number of rows and the same number of columns. Okay, all right. So that's matrix. And once we have a matrix, so when we have vectors, we defined the inner product. Now when we have matrix, we can define multiplication. So if we take two matrices, A and B, and the requirement is that the number of columns in A should match the number of rows in B. Okay? If this is the case, then we can define the product, which is a matrix with the same number of rows in A and the same number of columns in B. Okay? And the I case entry of the product is given by this summation here. Okay? And the summation is over the common index J. You have the same number. This n is the number of columns of A and the number of rows in B. So you can do the summation here. Okay? And if you take two column vectors and treat them as a matrix, then you can actually easily show the dot product or the inner product between them is the U transpose V when you treat U and V as D by 1 matrix. And you can easily prove AB transpose equals B transpose multiply A transpose. This is very easy. I leave this for yourself. And we can also have a row interpretation of the matrix multiplication. Namely that if I look at the I case entry of the product, what I'm doing basically is if I write, we have A and we have B, right? What I'm doing is basically I'm taking the ith row and I'm taking the case column. They have the same size, so I just do the dot product of these two vectors of the same size. That gives me a number, and that number is the I case entry of the product. There's another way of looking at the matrix multiplication, namely that I can look at the first matrix as columns, and I take the second matrix as rows. Okay? And then I take the first column, I multiply the first row. I take the second column, I multiply the second row. Each time I'm going to get a matrix, and I'm going to sum all of these matrices. That will give me the product again. The difference is here this is a dot product that gives you one number. Here this is a matrix, and you have to sum these matrices to get the product. Okay, so these two views of matrix multiplication are both useful. And the definition here, because here we have n summations, and this only gives us one entry in the matrix C, and we have n multiplied p entries. Therefore, the number of computations we have to do is mnp. Right, that's clear. And there exist faster algorithms for performing the matrix multiplication. And the interesting thing is that we still do not know what is the optimal algorithm for performing matrix multiplication. It is one of the major open problems in computational complexity. Okay, so once we have matrix product, we can define the inverse of a square matrix A. Okay, and it's defined if AB is identity, then we call B the inverse of A, or A is the inverse of B. Okay, and we use this notation to indicate B is the inverse of A. And of course, if B is the inverse of A, then A is also the inverse of B. And you have AB inverse equals B inverse multiply A inverse. And A transpose inverse equals A inverse and then transpose. Okay, all of these are basic rules. I'm sure you have seen them before. Alright, so once we have matrix multiplication, we can also define eigenvalues. So we say a complex number lambda and a complex vector v, the eigenvalue and the eigenvector over square matrix. Okay, it only applies to square matrices if the following is true: a multiply v equals lambda multiply v. Okay, so this is a vector, this is also a vector, so you can match them. And it is known that every matrix has n eigenvalues. So if a matrix has size n by n, then it has exactly n eigenvalues if we count multiplicity. And for real matrix, the eigenvalue and the eigenvector can be complex. Okay. However, if you have a real symmetric matrix, then the eigenvalues and the eigenvectors, they can both be chosen to be real. Okay, they consist of real numbers. And in this case, you can also show you have exactly n orthogonal eigenvectors. So you have n eigenvectors, and they're orthogonal to each other. Okay, some people call this an eigenbase. And we say a real symmetric matrix is positive semi-definite if all of its eigenvalues are non-negative. If values are strictly positive, then we call the matrix positive definite. And we use this notation to mean that the symmetric matrix A is positive semi-definite, and this is for positive definite. Okay, and similarly, you can define a negative semi-definite when all the eigenvalues are non-positive, and we call a matrix negative definite if all the eigenvalues are strictly negative, right? And we call real symmetric matrix indefinite if it has a positive eigenvalue and also a negative eigenvalue. Okay. And finally, we say the singular value of any matrix, it doesn't have to be square now, is defined as the square root of the eigenvalues of A multiply A transpose. Okay, so A transpose is always a symmetric positive semi-definite matrix. Eigenvalues are always non-negative. That's why you can take square root. That gives you the singular value. So the singular value is always non-negative. Okay, unlike the eigenvalues. Okay, so that is the eigenvalue of matrices. One word about the notation. So throughout the course, I'm going to use lowercase letters for numbers or scalars. And I'm going to use boldface lowercase for vectors. And uppercase are used for matrices. For example, we use the capital letter A for a matrix with certain size. And then we're going to use AJ, the boldface AJ, for the J's column of the matrix A. And then we're going to use the non-bold AIJ for the IJ's scalar entry of the matrix A. Okay. And sometimes we also use a bold A with the index J. And I want to emphasize that a boldface A sub index J is very different from AJ without the boldface. Okay, AJ without the boldface is a J's entry of the vector A, whereas the boldface AJ is another vector that may have nothing to do with the vector A. Okay, so if this is the first time you see these notations, it can be confusing. But after a while, you will find this distinction to be convenient and useful. Okay. All right. Next, I will recall the definition of norms. In particular, the Euclidean norm or the L2 norm of a vector is defined as the square root of the dot product. If you recall, in the Cauchy-Schwarz inequality, we had this term, right? So now we can actually replace that term with the L2 norm or the Euclidean norm. The Euclidean norm is simply the square root of the summation of the square of the entries. And more generally, you can define the LP norm as the summation of the absolute value to the power of p, and then you take 1 over p root. And if p equals infinity, then you just take the maximum of the absolute entries. Okay? And you can verify the Euclidean norm or the LP norm satisfy the following properties. So a norm is always non-negative with equality if and only if the vector is 0. And if you multiply a vector with a scalar alpha and you take the norm, then it's the same as the absolute value of the scalar multiplied the norm. So you can basically pull the scalar out, taking absolute value. And we have triangle inequality, namely that if you add two vectors, then their norm is always smaller than the sum of the norms. Okay? In fact, these three properties are the definition of an abstract norm. Okay? So any norm, any function that satisfies these properties, we're going to call them a norm. All right. And this is a core theorem in linear algebra, namely that all norms are equivalent. So this basically means if you take two norms, okay, meaning that these two functions satisfy these three properties here. Okay, for instance, you can take the L2 norm and maybe L3 norm if you want. Okay, and take any arbitrary two norms, then there always exist two constants, such that for any vector we have these inequality. So one norm is sandwiched in the other norm by these coefficients. Okay, and the key here is these coefficients, these numbers CD, they do not depend on the vector V, but they do depend on the dimension of the space. Okay, and as you're going to see, a lot of algorithms that we study, they actually try to exploit the fact that different norms, they may give you a different convergence rate of certain iterative algorithms. So sometimes we have to choose a proper norm for our algorithm and for our problem. Okay, so we'll see examples of this later lectures. All right, and you can also define a norm for matrix. For instance, if you take a matrix A, you can actually turn that matrix into a vector. For instance, you can take all the columns of a matrix, right? So if I have a matrix A, I have these columns in a matrix A. What I can do is I can just take the second column and put it here, take the third column, put it here, take the fourth column, put it here, and now I can get a vector, right? And once I have a vector, then I can apply any vector norm that gives me essentially a matrix norm. For instance, if you take the vector L2 norm, then you get the so-called Frobenius norm of a matrix. Okay. We can also define the so-called induced norm. Okay. Here, basically, what you do is you take a vector norm, and then you define the induced matrix norm as the maximum of all non-zero vectors, and then you have the ratio between the norm of two vectors, right? The first one is AV, the second one is just V. Okay, this is a definition. And a very good exercise for you is to show that this induced matrix norm is indeed a norm. So this definition here indeed gives you a norm. Okay. And if this is the first time you see the induced norm, you may wonder, why do I have these inequalities? And the reason is because, which is quite simple, the reason is that if you look at what we have, you can say this is equal to max v not equal 0, and I'm going to have a multiply v divided by v. So basically we're using the homogeneity of a norm, right? We can push this denominator inside the norm. And then you do a change of variable, right? I'm going to change this, and this, do a change of variable. Let's say I call this u. Then I know the norm of u is just 1, right? And that gives you this side. And these two can be seen to be equal because you're maximizing, so it always makes sense to set the inequality to equality. Okay. All right. In particular, if you choose this vector norm to be the L2 norm, then the induced norm will give you the largest singular value of the matrix A. Okay. So in some of the algorithms that we're going to study, when we need to choose the step size usually can be chosen as some quantity related to the spectral norm or the large singular value of certain matrix. Okay, we'll see that in later lectures. All right, so now I basically have done linear algebra, so I'll move on to calculus a little bit. First, I'll define what is a gradient and what is a Hessian. Okay, so we're going to have a function f that takes a vector in Rd and maps it to a real number. And I'm going to assume the function f is smooth, namely that it's differentiable, maybe it's twice differentiable. Okay, so the gradient of the function is just a connection of partial derivatives. So you take the partial derivative with respect to the first input, and you take the partial derivative with respect to the second input, and so on and so forth until you take the partial derivative with respect to the d's input. Okay, so you get d partial derivatives, and you put them together, you get a vector of size. Okay, and that is your gradient. So the important message here is the gradient always has the same dimension as the input. If the input is in Rd, the gradient is in Rd. Okay, later on you're going to see in gradient descent we're going to update by subtracting the gradient. Right? The reason we can do this update is because x as the input is in Rd and the gradient is in Rd. Therefore, we have two vectors of the same size, so we can subtract them. Okay, and the Hessian is defined similarly, except that it's a matrix. It's a symmetric matrix. So the Hessian, the ij's entry of a Hessian is the partial derivative with respect to I and with respect to j, and if f is twice differentiable, then we know from calculus that the ordering here doesn't really matter. Okay, and this basically implies the Hessian is symmetric. Okay, so here's the example shown here. We take a quadratic function. So the quadratic function is x transpose q. Q is a symmetric matrix or any matrix, square matrix. X is a vector, column vector. P is a column vector. Alpha is a number. And the input is in d-dimensional. Q is d by d. P is a t-dimensional vector, so we need to match all the dimensions, right? Alpha is a number, and if we compute the gradient is Q plus Q transpose X, and the plus P, and the Hessian is Q plus Q transpose. Okay. And if this is the first time you see this, there is a detailed calculation in the note. So I'm not going to repeat it here because it's quite tedious and not very insightful. But if you're not familiar with this, you should do it by yourself. You should try to compute the partial derivatives and the Hessian by yourself on this example. Okay, so you can actually write down the function as sum of ij xi xj qij plus sum of k pk xk plus alpha. Right, you can do the partial derivatives all by yourself, and to verify this is true, this is true. Okay, so you must do this exercise by yourself if you haven't done it before. It's super important. And once you verify this, you need to memorize this result, because we're going to need this again. Okay, it doesn't make any sense to repeat the calculation every time. Okay, and I want to remind you that at least in my machine learning course, I always have students, mostly undergrad students, who are not able to compute partial derivatives of even very simple functions. Okay, so you guys are graduate students, so I hope this computation of the gradient or computation of the Hessian is relatively straightforward to you. Okay, you just need to be patient. Okay, and the last thing is that when we actually implement algorithms, we're not going to compute the gradient by ourselves. Okay, there will be packages that we can use, but you still need to be able to compute the gradient of simple functions, because sometimes it's handy if we want to analyze certain things. Okay, so that's all I want to say about the gradient and the Hessian. As I mentioned, there is a fancier definition in the note, which you do not need to understand. There's also a detailed example in the note, so you can always check that. Alright, so now I'm going to move on to convexity. Okay, so when we discuss our optimization algorithms, we will distinguish two scenarios. One, what happens if we apply the algorithm to a convex function, and two, what happens if we apply the algorithm to a non-convex function. So we have such a distinction because convex functions are super nice, as you're going to see here. Okay, so let's try to define what do I mean by convex function. So we start with a convex set. If you take a subset of Rd, it's just connection of points of vectors, we say this set is convex if you take any 2 points from the set and you connect the 2 points by the segment. So I use this notation as the line segment that connects these 2 points. So if you have x, if you have z, the line segment that connects the two is basically written here. Okay, and I'm going to call this line segment as convex combination of x and z. Okay, so the exact formula is here, where lambda has to be between 0 and 1. Okay, so the set is convex if whenever you take 2 points from the set, the convex combination is also in the set. Okay, you cannot go outside of the set. So here's an example, like in A, this set is not convex because if I take 2 points in the set, then the convex combination contains points that is not in the set. therefore it's not convex. On the other hand, if you look at the right figure here, this is a convex set because if you take any 2 points, you connect them, it's still in the set. Okay. And this is a very nice property, namely that if you intersect convex sets, then it's still convex. On the other hand, if you take unions of convex sets, then it may not be convex. This is super clear. For instance, if you take a convex set, you take another one, obviously the union is not convex. Okay. And we can also define a half space. So a half space is basically take a line, and one side of the line is called a half space. Okay, we have seen this in the introductory lecture. And if you take a finite intersection of half space, then you get the so-called polyhedron. Okay, like here, which this area is a polyhedron because we have 1, 2, 3, 4, 5 half space. We intersect them. Okay, and any convex set is actually an infinite intersection of half spaces. For instance, this ellipsoid here is the intersection of infinite many half spaces. Okay, you can actually cut the ellipsoid. Okay, so this tells you convexity is really about intersection of lines or half spaces. Alright, so once we know what is a convex set, now we can define a convex function. A convex function from a set C to the real number is convex if its domain C has to be a convex set. Okay, the domain has to be convex in order for the function to be convex. Then you take 2 points from the domain and you take the convex combination. Then the function has a smaller value at the convex combination than the convex combination of the function values. Okay, and we call the function strictly convex if this inequality here holds if and only if the 2 points coincide. Okay, and similarly we call the function f concave if the negation is convex. So here's an example. On the left, we have a function, which is this function here. This is convex because if you take 2 points, x and y, then you take a convex combination, right? The value here, this value is basically the right hand side. And if you look at this value, this is basically the left hand side. So this is the left hand side, this is the right hand side. Okay, so you can see the right hand side is always greater. So this means whenever you take 2 points and you connect them, the chord always lies above the graph of the function. And for concave functions, it's the opposite. 2 points, you connect them, then the chord always lies below the graph. Okay, so quite intuitive, the definition. So how do I verify if a function is convex or not? Well, if the function is differentiable, that's quite easy. You take the function f and you take the Hessian. You take the gradient of the gradient, basically, the Hessian. And if the Hessian as a matrix, a symmetric matrix, in fact, if it is positive semi-definite, so meaning that the Hessian always has non-negative eigenvalues, then the function f is convex. Okay. In fact, this is the if and only if condition if f is twice differentiable. Okay, and if the Hessian is always positive definite, then f is actually strictly convex, although the converse is not true here. And the example is shown here. So we have a function x to the power of 4th. This is a strictly convex function, but its Hessian or second order derivative can actually vanish. Okay, so it's positive semi-definite but not positive definite at the origin. Okay, So you can also think of convex function as the following. If you take a direction and you look at how the function behave along that direction, then the function along that direction has always increasing derivative. Okay, so along that direction, if you take the derivative, then the derivative always is non-negative. It's like the derivative is always increasing. So if you take the derivative of the derivative, then it's always non-negative. Okay. All right. So, and there are quite a few rules about convexity. Okay. For instance, if you take any norm, then it's convex. And if you define the so-called AB graph, namely that you take a graph of a function and you take anything is above the graph, then it's called an AB graph. Okay, and the function is convex if and only if the AB graph is a convex set. So there is actually an equivalence between function and set. And if you take two convex functions, then and you take non-negative numbers alpha and beta, then this linear combination is convex. On the other hand, the negation of a convex function is not convex, it's concave, right? And if you compose the function with a linear function, then it's also convex. If you take the maximum over some convex functions, then it's convex. And if you take the minimum, it is also convex, but only when the function is convex in terms of x and t as a whole. Okay. And finally, this perspective function defined this way is jointly convex in x and t if f is convex. Okay, so these are very useful rules. Once you get familiar with them, and you can combine with this theorem here, so these then you can easily verify as many functions, whether or not they're convex. In the note, there are quite a few examples. Okay, so you should try to verify the convexity of those functions by yourself. Okay, you should feel free to use these rules. Okay, so now finally we come to optimization. Okay, so if we have a function f, we can define a minimization problem, namely that I want to minimize the function f over some constraint c. So here constraint means I only consider points x in that set C. Any point that's not in the set C, I would not even consider them. I cannot consider them. Okay? And I'm using this inf instead of minimizing for rigorous reasons. So here's an example why we use inf. Okay? You take the exponential function e to the x. So if I draw the graph, this is a function. And if you try to compute the minimum of this function, what is the minimum? Where x is a number, right? The answer is no minimum, because it doesn't matter what number x you pick, I can always pick another one that gives you a smaller function value, right? But we do know e of x approaches 0, right? And this is why we use inf. So if I write inf e of x, I can say this is 0. Okay, inf means you can actually approach. You do not have to equal to 0. Okay. On the other hand, there does not exist any real number x such that ex equals 0. Right? There is no such x. So there is no minimizer, but we have a minimum value. This is why we usually use inf. And machine learning people typically are not very careful about this, but optimization people are very careful. So whenever we write inf, we mean we do not know if we can approach the minimum, And when we write min, that actually means we know it's possible to achieve the minimum value. Okay? So the minimum value is always a number, right? And sometimes people write the minimum value to be infinity if the set C is the empty set. Okay, this is just a definition. Okay? And any feasible x in the set C such that its function value achieves the minimum, then we will call x star a global minimizer. Okay, so x star minimizes the function f because f attains the minimum value at this point. Okay, to give you another example, if we take a quadratic function like x squared, then x squared plus 1, let's say, so that my figure is correct. So then I can say x equals 0 is the minimizer of this function, right? Because the function attains the minimum value at x equals 0. Okay? The important thing is minimum value always exists, but minimizer may not, right? So the exponential function is the example. The minimum value is 0, but there does not exist any minimizer. Okay? And in the note, I give you a theorem where you can verify if a given problem has a minimizer or not. Okay? In most parts of this course, we will not be super careful about the existence of minimizers, but you should try to get into the habit. You should always try to verify if a given problem has a minimizer or not. And if a point minimizes a function over a small neighborhood but not over the entire set C, then we call this x star a local minimizer, right? It's only the smallest or the minimum in a small neighborhood but not in the entire set C. Okay, and obviously a global minimizer is a local minimizer, but the converse, a local minimizer is also global, is true only when the function f and the set C are convex. So this is proved in the note, so you can check if you're interested. Okay, and this is why convexity is super important, right? So we have two functions on the left and a non-convex function on the right. And you can see for convex function, this point, the red dot here, is a minimizer in a neighborhood, but it's also a minimizer in the entire space, right? On the other hand, if you have a non-convex function, for instance here, this point is a minimizer in this neighborhood, but it is not a minimizer in the entire space because it's another beta one, right? And for non-convex function, you can also have a point where the gradient is 0, but it's not a local minimizer. Okay, these points are called a saddle point. And later on, when we discuss gradient algorithm, we'll see how to avoid getting trapped at a saddle point. Okay, so a saddle point is when the gradient is 0, but the Hessian is indefinite. Okay. All right. So here I'm listing some properties of minimizing, maximizing. I'm not going to read this carefully, but what it basically says is, for instance, if x star is a minimizer, I'll just give you an example, f, then x star is also a minimizer of, let's say, 2 multiply f. Okay, that's quite clear, right? If you scale everything by the same constant, then you don't change the minimizer. Okay, but you do change the minimum value. The minimum value of this 2 times f is twice of the minimum value of the function f, but the minimizer remains the same. Okay, and there are some other properties which are very similar to what I just said. So you should go through this by yourself, and they are quite obvious. Actually, prove all of them by yourself. Okay, so now I can state one optimality condition. So next time we're going to actually analyze an algorithm that can achieve this optimality condition. So this is known as Fermat's necessary condition, namely that if you have a differentiable function f and we want to minimize this function f, this function f may or may not be convex. And if we want to find a no-co minimizer, then a necessary condition is that the gradient has to vanish at a no-co minimizer. Okay, and these points are actually, so this is a necessary condition, meaning that a point satisfying this condition may not be a no-co minimizer, but any no-co minimizer has to satisfy this condition. Okay, that's why it's called a necessary condition. And these points are actually called stationarity. Okay, stationary or critical points. So we can actually say any no-co minimizer is stationary, but not all stationary points are no-co minimizer. If the function f is convex, then this necessary condition is also efficient. So you see, convexity is really an important property, right? It rules out the existence of no-co but not global minimizers. And you can also show at the no-co minimizer, the Hessian has to be positive semi-definite. Okay, so from here you can actually classify stationary points. So you have a stationary point, namely that the gradient vanishes. Then you have the Hessian is positive semi-definite, and the Hessian is negative semi-definite, and you have the Hessian that is indefinite, right? And this almost implies it's a no-co minimizer. This almost implies it's a no-co maximizer, and this almost implies it's a saddle point. Okay, I said almost because if there are degenerate cases, okay, what you can say is if it's positive definite, then it's a no-co minimizer. If it's negative definite, then it's a no-co maximizer. Okay. All right. So why Fermat's condition is cool? Well, because it gives us a goal to optimize, right? As we're going to show you next time, minimizing a non-convex function is difficult. So there's no way we can verify, if we achieved our goal or not. But we can verify Fermat's necessary condition, right? I have an algorithm where I can come up with some candidate solution x. And then I just compute the gradient at x. If the gradient at x is super small, then that means I'm very close to stationarity. And that is a necessary condition for no-co minimizer, right? So the gradient descent algorithm that we're going to analyze next time, they actually try, it actually tries to satisfy Fermat's condition. Okay, and I want to emphasize that if you want to apply Fermat's necessary condition, you cannot have any constraint. Okay, the function has no constraint at all. So here's a counterexample. If you're minimizing a smooth quadratic function, but you have a constraint, x has to be greater than 1, then it's obvious the minimizer is just x equals 1. But if you ignore the constraint and you apply Fermat's condition, you take the derivative of x squared and then you put the derivative to 0, you get x equals 0. The x equals 0 is not even feasible, so it's not a local minimizer. Okay, so we can apply firmware condition only when there is no constraint. Okay, and later on in the course, we're going to study algorithms that can handle constraints. Okay, for now, for firmware condition, you cannot have any constraint. But later on, we're going to see how to handle constraints, okay, in different ways. Okay, so this is the algorithm we're going to analyze next time. Here, I just want to show you how the algorithm looks like. Basically, it's an iterative algorithm, right? So we have iteration. Then in each iteration, you choose a direction and you choose a step size. So the direction is a vector, step size is a scalar, and then you just do the update. Okay, and if you have a constraint, you can do the so-called projection so that you can stay in the constraint. Okay, and just keep doing this. Then eventually, we're going to show you're going to converge to you're going to satisfy a firmware condition eventually. Okay, and the key is that you do a Taylor expansion, and then you show that if the step size is chosen appropriately, then you can actually reduce the function value. Okay, and some people call this algorithm is descending because the function value is decreasing. Okay, and typical choices of the direction includes the gradient or the inverse of the Hessian multiplied gradient. This is called the Newton's algorithm. We may come back to Newton's algorithm in the end, towards the end of the course. And we also study stochastic gradient algorithm, where the direction is a random variable, but the expectation of this random variable is a gradient, or maybe it's the Newton update. Okay, and we also study algorithms that can reduce the variance in the stochastic gradient descent algorithm. Okay, there are also a variety of ways to choose the step size. So I'm not going to give you details here. Next time, we're going to analyze one or two of these rules. Okay. All right. So some subtleties about the gradient descent algorithm. We have examples in the note, so you can actually check. So the function value f of xt typically will converge under very mild assumptions. But the iterate xt itself may or may not converge. Okay, and the good news is now we actually have techniques, very under very mild conditions, we can actually show xt will also converge. Okay, and a common mistake for people who probably have never taken an optimization course is that they often mistake the convergence of fxt with the descending property. Okay, so if I have an algorithm where I can decrease the function value in each iteration, I strictly decrease the function value at each iteration, does that mean I will converge to a stationary point? The answer is no. Okay, and there is an example in the note, but here let me just give you a very simple explanation. For instance, if you take the series 1 over n squared, take a summation of n. Let's say n equals 1 to k, and this is sk. Then you can easily convince yourself sk plus 1 is greater than sk. Right? So at each iteration, I'm going to strictly increase sk. But this does not imply sk will converge to infinity. Right? In fact, sk will converge to a finite number. And basically, you can use this to construct an example where the algorithm, even if you can decrease the function value strictly in each iteration, you may still not be able to converge to a stationary point. Okay. And even when you can show that the algorithm converges to a stationary point, it still may not be a local minimizer, right? And in this case, some very recent work has shown that if you add some randomness to the problem, then almost surely you can show you will converge to a local minimizer. Okay, so we'll actually maybe see this proof later on. All right, so that is what I want to show you about the gradient descent algorithm. So next time we're going to analyze it, and we're going to formally explain everything. So here I'm just giving you a big picture of what kind of algorithms we're going to implement and analyze. So a second algorithm that we're going to analyze is the so-called gradient descent ascent algorithm. This algorithm is used for minimax problems. So you have a minimization problem and you have a maximization problem. Okay, and the algorithm is extremely simple. Basically, because I'm minimizing with respect to x, I just do a gradient step on x. Because I'm maximizing over y, I do a gradient step on y. I'm going to add because I'm maximizing, right? And that's it. This is the algorithm. And you can easily prove this algorithm typically will not work. Okay? And in fact, another recent work in machine learning, in particular in generative adversarial works, people apply the gradient descent ascent algorithm, and there's a lot of heuristics about how to fix the algorithm. But this is actually well studied in optimization. So we're going to see some of the classical analysis and classic sort of variants of this algorithm that are guaranteed to converge. Okay. In particular, there is a very simple trick called averaging. So you just run this algorithm, it will not converge, but if you actually average the trajectory, then it will converge. So here's an example where we run the algorithm on a very simple example, and the example is in the note. And you can see if you run the gradient descent ascent algorithm, it will oscillate. So basically on the left, you see this is the update on x, this is the update on y. It's oscillating. Okay, so you will not converge, but if you actually average the trajectory, then you see it will converge to the solution. Okay, so you can average things in different ways. This is the averaging. Basically, you take every point you have seen, you just do uniform averaging. Okay, so x. Okay, here you just do a different averaging here. Okay, both of them will work. There are also quite a few variants of this algorithm, so we'll discuss some of them in later lectures. All right, so there's also another algorithm that we're going to analyze. This is called alternating. So this is for the problem where you have a minimization over x and a minimization over y. And the algorithm works again extremely simple. You fix y, you try to find the optimal value for x, and then you fix x, you try to find the optimal value for y. Okay, it's extremely simple. So now if I'll give you an example here. This is a very simple example, and I hope you can easily see the minimizer is either 1 minus 1 or minus 1 1. Okay, and the way to say it is, if you look at here, this is basically minus x absolute value. And now you're minimizing, therefore x can be 1 or minus 1, and y can be minus 1 or 1. Okay, it's clear that we have two minimizers. Now if you apply the alternating minimization algorithm, then you actually converge very quickly. For instance, if you select x to be greater than 0, then if you fix x, because x is positive, then y should be minus 1 in order to minimize. Right, so y is minus 1. So now if you fix y to be minus 1, then for x to be minimizing, then x should be 1. And then for x to be 1, if you want to minimize y, y should be minus 1. So we have converged. Okay, and indeed, this 1 minus 1 is an optimal solution. Okay, so the alternating algorithm works for this example. And the one common mistake in, at least in the machine learning field, is that people try to use the alternating algorithm for minimax problems. So when you have a maximization problem over y, the problem is alternating does not work. Okay, for minimax problems, it works for min problems. And here's example: if you have a minimax problem, and trust me, the solution for this problem should be 0, 0. Okay, later on we're going to explain why, but not today. And if you start with positive x, and if you fix x, you solve for y, because x is positive and we're maximizing, y should be 1. And you fix y equals 1, minimizing x, then x should be minus 1. And then you just keep iterating, you will realize that you have a cycle. So you have minus 1, 1, 1, minus 1, minus 1. Okay, so we have a cycle here. And this cycle is bounded away from our solution. Okay, so whenever you apply alternating to a minimax problem, you will have a cycling issue. And this actually was reported a lot in the machine learning literature. And the interesting thing is, and it's for this example, if you take this cycle, you average the trajectory, then again, it will converge, right? If you take this minus 1, 1, minus 1, 1, and if you average it, you'll go to 0. Similarly for x, right? If you average it, you will go to 0. So this is very interesting, right? You have an algorithm that does not work, and if you average it, it will work. Okay, so we're going to make this formal. We're going to analyze them. We're going to prove when do they converge, when do they diverge, and if they converge, how fast will they converge. Okay. Yeah, so that is what I want to discuss for today. I know there's a lot of material. We went through a lot of technical terms. So as I said in the beginning, it's okay if you felt a little bit overwhelming. The good news is we don't really need most of the material for the next lecture, for instance, right? So you will have time to digest everything. And in fact, we're going to, for the algorithm I mentioned, we are going to analyze them in more details. Okay, and you're going to implement these algorithms on more complicated examples. Okay, so that's all I want to say for today. Thanks for listening, and I'll see you next time.